In this video lecture, we're going to discuss the rotational dynamics associated with a pulley over which is stretched a string, at the end of which is a hanging mass. At the other end, on a tabletop, is a block that will slide on a frictionless tabletop. Our goal is to discover three things: the acceleration of this block and the tension on either side of the pulley. Let's look at the sliding block first. We'll apply Newton's second law to it. Symbolize that block's acceleration as A. That acceleration points to the right, so it will be some positive number. And we have, from Newton's second law, the only force acting on that block is the tension, T1 will symbolize it, in that string. And so we have the force is T1 equaling m times A. That's our first of three equations that we will develop to correspond to the three unknowns that will appear in this problem. Now let's take a look at the falling mass next. The falling block experiences an upward pull due to the string. That upward pull equals the tension in the string on this side of the pulley. Give it a different symbol name, T2. And so there will be a tension force acting upward and a pull by the earth downward, whose magnitude is mg. We'll later take into account that that force points in the negative direction. The acceleration of this block is going to be a negative number. The magnitude of that hanging block's acceleration will be the same as the magnitude of that block's acceleration, since they're moving as a unit. Whatever one does, the other does, but in a different direction. So if this symbol represents this block's acceleration to the right, the negative acceleration that this block has is negative A. Now we'll apply Newton's second law to the hanging block, and we have the sum of the forces is T2 positive upward. Subtract mg, the downward pull by earth, and that equals m times the acceleration of the block, which we have symbolized as negative A. That will be the second of the three equations that we need to solve for the three unknowns. The third equation comes from an application of Newton's second law in its angular form. Tau, the analog of F, equals I, the analog of M, times alpha, the analog of A. Now, the torque, net torque acting on our pulley, is found from this diagram, which is an enlarged view of the pulley. There's the center of the pulley, the radius of the pulley. At the top of the pulley here, there is a tension force which, if acting alone, would cause a counterclockwise rotation. And so its torque is a negative number. Whereas here we have the tension in the string T2 applying a torque that would cause a clockwise rotation, so its torque is positive. Remember how torques are calculated. It's the length of the radius arm, the length of the lever arm, which points from the axis of rotation, which is at the center of the pulley, the distance between that point and the point of application of the force. The force in question is T2. So the torque due to this is R times T2. That's the first of the two torques acting. The other torque is negative R times T1. and that equals I times alpha. Rather than put an alpha there, I'll take the opportunity of using this relationship here, where alpha is proportional to A, and so instead of alpha, I'll write A over R. Now you see exposed in this one equation here, the three unknowns that are part of this problem. A, T1, and T2. The other symbols have values you can assume that we know, such as the radius of the pulley R, the rotational inertia of the pulley I, and now we put a box around this equation. And that's the third of our three equations. What we can do is to substitute for T1 here and T2 from this equation to get a single equation involving A. All the other terms in that equation, which involves A and only A, are numbers whose values that we can assume that we would be given. In this example, we will not give numerical values for the masses lower m, upper m, and the radius of the pulley and the rotational inertia of the pulley, which you recall I've symbolized as I. The final result, I'll leave it for you to determine, to get the expression for A in terms of the known or presumed knowable values of the radius of the wheel and the various masses and I.